Now we're going to discuss the concentration analysis and what we can do, or how we can do a concentration analysis or a contamination analysis. It can be applicable for carbon dioxide for ventilation, example, or it can be like a dangerous lethal gas or CO, carbon monoxide in a parking, etc. This analysis can be done based on any condition, or you need to do the manual uh, analysis for it based on any condition. Then you will take the CFD, which is going to show you what is the effect of equipment inside, the location of the point of exhaust, point of makeup, for is it a uniform distribution. So, but you will have an idea what is your flow required. This is, by the way, it is if it is dangerous gases, so diesel gases to be like from 20 to 25 exchange, and sometimes 30 exchange, like if you have ozones, etc. So how we will do this calculation? Of course, the first assumption here is that is the gas is its scalar is way infinite, which is mean whatever you are taking, it is whatever you're injecting in the gas, it is almost homogeneous everywhere, which is the scalar is infinite. Okay, it's not the case, and we're going to discuss how we'll do the scalar calculation. CFD will cover this point also as well. Okay, but this calculation will give you an idea, the manual calculation, what is the result you get, or what is the input you should provide to be near by the success. As we understand that is simulation like this maybe will take time for 5 days or 2 days of running the computer, so to save computing power. Okay, its assumption or its basic of analysis is you assume, or you have an area or volume, and you have a mass inflow, and you have a mass outflow, and you have a generation of a gas inside. You know also that is a mass inflow coming from outside, which is having some gas, or it can be zero, and you push it out to outside. Okay, okay. Like what? Like CO2. You know that the CO2 outside is 400 ppm, and maybe the CO2 inside reach to 800 ppm, so you increase the ventilation to reduce that CO2. Okay, and you know there's persons still living or sitting in that hole and giving a generation of the CO2. This is an example about it. So the concentration outside, it is Ca. Concentration initially here, it will be C initial. Concentration at any time, we'll take it as C. This one is a ventilation, Q, whatever N is out. Okay. GC, it is the ppm produced in a volume count in second. Okay. It is a ppm produced in a volume counted in seconds. Okay, how to calculate it? At any time, the change in the concentration here in this room should equal to what is the mass flow rate, or what is the volume flow rate, multiply by its concentration, multiply by its concentration from outside, plus 10 to the power 6, which is changing for ppm, part per million. Part per million, it is mass per mass, by the way, which is dimensionless. Okay, so part per million, it will be mass per mass. Mass of CO2 divided by mass of air, okay, which is the ppm, all multiplied by dt over mass. By the way, the concentration, it can be go like this. The mass can go here, and the concentration, we know it is ppm. It is mass of CO2 example divided by mass of air. So the mass of air, if it is multiplied by the concentration, it becomes mass of CO2. So imagine this one, change in the mass of the CO2 is equal to the volume flow rate multiplied by the concentration. Oh, it will be here like this, mass flow rate, okay, multiplied by density, and etc. can continue, okay, multiplied by delta T, okay. And also you know that is the contamination leave, which is you push it out, it is same. The change of the concentration due to leaving air, it is how much air has been gone with its concentration multiplied by C, concentration of that room, at a certain time dt over m. So the total change is dc is the change in concentration is qc, all of this term, plus all of this term, common dt by m. So dc by dt equal all of this. I just put the dt there. So an integration from a concentration initially to a certain concentration is equal to, it is just it is algebra, by the way. It is like you put the m common and you put all of this term there. It is from 0 to t 1 over m dt, which is, we can state that, you can write that is, I can get the q common outside because q is constant as per the selection of q, okay, outside from c initial to c at a certain time, 1 over c minus ca outside ambient minus 10 to the power 6 g over q, because there's no q by q, dc equal t over m, goes from 0 to t, okay. This equation is very important, and this is the main equation that we're going to deal with, okay. Case number one, which is case exhaust g. I have an exhaust and g, which is mean I have exhaust, or I injected air or exhausting air, so the air will come as a makeup, and g is running, which is a general case. So make the integration. How you will make the integration? Make the integration in c, only c here is change, remaining is not change. So 1 over c, it is, its integration is ln divided by this one, and because we are it is ln this one minus ln this one, because it is ln this one, but when you apply the limit of the integration, so it is c minus c initial, which is c minus c initial, so ln minus ln, it is ln this over this. Then you will get algebra, this equation, just change the ln to e, so you will get this funky equation. So to calculate the concentration for the room at a certain time after 10 seconds, 1 million seconds, while you are taking air, flow rate is like this, and the mass of the room is like this, and you know that is at a certain time that is the concentration was 800 ppm, outside is 400 ppm, and you know that is the generation of the ppm per the flow is like this, okay. Or however, for example, it is you can state that is how many ppm is generated, okay, and etc etc etc. You will get the concentration after 10 seconds, 20 seconds, etc. But if you have exhaust and g stopped, that means there's a gas leak. When alarm happen, they stop all the equipment, and close the shut of the valve, then you start the ventilation, like LPG gas leak or ozone gas leak in a plant room. Okay, so it is the same concept, but put G is 0. Okay, put G is 0, you will get this equation. So okay, in case of no exhaust and still leakage happen, or still it is a confined room, there is people there without any changing of the air, put Q is equal 0. When Q is equal 0, just take care, don't put it here, because don't start to put Q common 0, so you'll have 1 over 0 is infinity and 0 is 0. You need to start it from this one. So if this one is 0, because otherwise you will create mathematical errors. Okay, so this one is 0, this one is 0, it is 1 over 10 to the power 6 G dc. It is all constant in front of dc. So when you will make the integration, it is C equal 10 to the power 6 G times C multiplied by concentration. And by the way, this is logic, huh? How the concentration is the initial concentration plus what? Mass ratio, because this one is a mass ratio between CO2, for example, and air, divided by mass air. So it will become a mass ratio, right? It is a mass ratio. And remember that this one is, its definition G is what? It is a ppm per second going to be injected. Okay. Of course, to calculate it, for example, if I said that the human being is generating, for example, 1 gram of CO2 per second, divide the 1 gram by the grams of the air of the room, so you will get G. Okay, this is how we calculate G. Okay. An example: there's a car CO, and the car emission is like this. CO2, it is, we know it is almost 14% from the emission, and we're going to check what is the reaction as species calculation, how we can identify this one, not by an assumption. Or we have a CO2 and the precipitation, if it is sleep is 0.3, if it is etc, which is meter cube per hour. And when you know meter cube multiplied by the density, you will get the mass, multiplied by, divided by the mass of the room, you will get the divided by ppm, but this is per hour, so divided by 3600 will get per second. Okay. So this is an examples of numbers which you need to consider. Okay, in case of an exhaust, or in case a whole or multi-purpose room. Okay. Also, points which you need to know, for example, CO2 maximum is 1000 ppm, and CO, it is maximum as per ASHRAE, it is 9 ppm, and it will be lethal if it is 35. That is why in the car parking we are defining CO sensor based on 2 levels, which is one is maximum as per ASHRAE or whatever, and one it will be lethal, which is you need to run the full speed. Some consultants doing it 10, 30. It is okay. Okay, now it is a new subject, or leakage analysis, pressure leakage analysis, pressure air leakage analysis, because we're going to have a thermal leakage analysis, and there is another stack effect analysis, and of course we're going to have super high-rise building filtration, which is combinations of outside wind, etc., chimney, plume height, the impact force. It is a little bit far away now from the fluid mechanics and CFD, but this is definitions you need to know it. Here we're going to concentrate on the some definitions in the CFD itself, not the fluid mechanics, in the CFD itself, and methods of solving, This is another subject, new one, which is diffusion and scalar calculation. If you, for example, the FM200 is have a high diffusion. The diffusivity for the FM200 is very high, and the diffusivity for example, for another gas like LPG is way less than FM200, for example, inside the air. And also it can be applied also for the smoke, for water, mist, etc. There's another subject for light visibility and species reaction. Okay, but we're going to stop here. And we're going to continue. Okay. Pressure leakage analysis, and better to stop here.